accomplished and which ones we have not accomplished yet, and what that implies. When is it all going to happen, and what does it mean to us as people? So, what most people think when you talk about AI is, well, if a machine can do it, and it's something that normally only a person could do in their head, then it must be artificial intelligence. But actually, um, a lot of what people consider artificial intelligence is really just being fooled by very clever tricks. And if you ask a computer scientist what artificial intelligence is, uh, what he'll often tell you is it's anything that a computer can't do. And as soon as a computer can do it, it's not artificial intelligence anymore. And I'll give you some examples of that in a little bit. Um, Philip, Adion, could you set your volume, turn off auto level, because I can hear you breathing. So today there are three things that are really driving AI. Back in the 70s, when I first got into the computer business, that was a long time ago, right? Um, Sorry, Louisa, I'm going to have to mute you too. Back in the 70s, Japan was very big into artificial intelligence, and they said that they would have artificial intelligence solved within 10 years. Well, that would have been the 80s. And of course, it didn't happen. And in fact, artificial intelligence kind of disappeared from conversation at around that time, because what they found out was they just couldn't do it. They didn't have the hardware to do it, but we do now. They didn't have synaptic processing units, cheap parallel processing units. And what these things grew out of was GPUs. And I'll talk a little more about GPUs and the like in a minute. But the first thing that we had to get was the hardware that would give us the capability of actually doing artificial intelligence. And we've come a long way with that. The next thing you had to have was lots and lots and lots of data. And I'll show you why that's necessary as well. And then the third thing is just, better computer scientists and better algorithms and things like that. It's just the natural learning process. So let me talk first about the processing units. The architecture in most computers today, almost all computers today, is an architecture that was designed by John von Neumann in the 40s. So it's really old. And it's worked really well all that time, but it doesn't work really well for artificial intelligence. There's a different kind of computer board called a GPU, a graphical processing unit, that was invented for video games. Because when you want to play video games, things have to happen with a lot of visuals, and they have to happen really fast. Like you've got a character who's animated and he's running down a hallway, right? Well, the way you animate a character is you have bunch of pictures of the character running, and the pictures, maybe there are 20 in a sequence, and then they just repeat. And as long as you keep running through those same 20 pictures over and over again, you've got a character that looks like he's running. So what they did with GPUs is every one of these little green squares here is a computer. And each one of those computers has memory associated with it. So what they can do is they can load into memory on each one of those computers one of those pictures. So they'll put the first picture, say, in this computer, and the second picture here, and the third one here, and the fourth one here, and so on. And then they just flip through them, 1, 2, 3, 4, 5, 6, and then they go back to 1 when they get to the end. And because they can just flip through them like that, you get real-time animation. It's great. And then maybe in the background, as he's moving through the background, you preload some of those computers with pictures of the background moving, and you get the animation there. So great design for games. It turned out that computer scientists looked at that and they said, wow, this could be used to simulate how the brain works if we used each one of those little green computers there as a part of a brain, doing what brains do, right? And it turned out the hardware was there. Why not use it? And they did, and they made a lot of success with it. And this particular GPU that I'm showing you here It's 16 by 16. That's 256 computers. Um, they get a lot bigger than that. 256 computers on a single chip is not a big deal anymore. It used to be. This is the newest chip from NVIDIA. It's called the A100. And the NVIDIA A100 is a pretty hefty piece of hardware. It's got 54 billion transistors on it. And the transistors are tiny. They're only 7 billionths of a meter in size. They're really, really small. They're so small, in fact, that computer chips are starting to run into quantum effects because the components are so tiny that something like an alpha particle from outer space can bang into one and disrupt what the computer's doing. That's how small they are. So there's a real question not right now, can these components even get smaller than that? Is it possible for them to get smaller than that? And most of the thinking is no, we're kind of at the end of the road. So if you want to do something that doesn't suffer from quantum effects, you invent something that uses quantum effects, and that's called the quantum computer. So that's the next wave that's coming. I'll talk about that a little later. The cores in this NVIDIA chip are called tensor cores, and tensor is the artificial intelligence design that was developed by Google. And Google is the world leader right now in artificial intelligence, at least I think so. I might be wrong about that, but NVIDIA took that technology, the tensor core, and they built it into this chip. And this chip has lots and lots of processing units in it. It's got 6,912 processors in it. So each one of those could simulate, say, a bunch of neurons, maybe 100 neurons in your brain could be simulated in each one of those cores. So in that regard, then it's simulating, 691,000 neurons, which be good, not bad. And it runs at very high speed, 19.5 trillion operations a second. So lots and lots of activity at very high speeds. It's got lots of onboard memory, and the memory is associated with each one of those cores in there too. Lots of memory bandwidth so the cores can communicate with each other. So really powerful stuff. You can take 8 of those boards and combine them into a single image, and then you've got the processing power of 5 petaflops. That's 5 times 10 to the 15th power operations per second. So a lot. Here's the latest one from Baidu. Baidu made a chip that they want to be used for edge computing devices. Like, what's an edge computing device? Your phone, your laptop. If you want your laptop to have artificial intelligence, you could put one of these Baidu chips in it and have artificial intelligence running on your laptop or on your phone or in your car. So that's their goal. Their chip runs at 260 teraflops, 260 trillion operations per second. This is the world's largest chip. This is a single piece of silicon, and it's got lots and lots of processors on it. 2.6 trillion transistors, 850,000 cores. Again, each one of those cores is there to simulate the functionality of a human brain or some part of a human brain. And again, we're down to 7 nanometers for the components of that. So the hardware is there today to do some very powerful processing, but none of them is as powerful as a human brain. A human brain executes 1 exo logical operations per second. That's 1 times 10 to the 18th. So you can see that's a pretty big number. And the human brain does all of this burning only 20 watts of power, which is very little. That's the, the little tiny light bulb in the back of your oven. That's 20 watts. That's all your brain burns. But these other chips and these large computers that do artificial intelligence burn thousands of watts. So another thing that the brain has all this hardware is we're very energy efficient. The next thing that we needed in order to accomplish what we have in artificial intelligence is data. The amount of data we create every day now is 2.5 quintillion bytes of data. That's 2.5 times 10 to the 18th power. That's a lot of data. This data comes from everything you do that's related to a screen, and sometimes not even a screen. Um, when you download a new app onto your cell phone and it asks you, do you accept this agreement that you didn't read? And you click, yes, I accept, right? What are you going to do to me? I accept your agreement. What you're buying into is you're saying you can collect all the data that I look at on my cell phone, and you can record my voice if you want to. And everything I do when I browse the web, you can collect that information. When I go on Facebook, you can get all my pictures. You can look at everything I post. You can find out what I had for dinner and who my cousins are. And you can have all that information. And all that information is being collected at this incredible rate of 2.5 quintillions of bytes of data per day. And there's a saying that's been coined lately: if you don't know what the product is, you're the product. So when you download that free app, the reason they're giving it to you for free is because they want your data. And I'll give you some examples of what they do with that data in a little while. But one of the things they do with it is they use it to train artificial intelligence. So one of the reasons Google is so far ahead of everybody else is because Google's got more information, more pictures, more data than anybody. To clear up one confusion, a lot of people confabulate robots and artificial intelligence. They're not the same thing. A robot can be connected to artificial intelligence. It can be driven by artificial intelligence, but the robot is not artificially intelligent. There are robots out in the world. You see them on TV, you see them in YouTube videos, dancing, walking around. They don't generally have artificial intelligence on board, because artificial intelligence takes a pretty large computer on which to run, and it burns a lot of power. And robots run on batteries. So we don't have the battery technology to support a powerful robot running real AI on its back or in its head today. So most of those robots you see, they're being run by an artificial intelligence that's somewhere else. So you can think of AI as being your brain and robot as being your body, right? So when you see a robot in a movie like Ex Machina, and she's real slim and she walks around and she's very well coordinated and everything, that can't actually exist today, because where's the battery to power that thing for more than 40 minutes, right? It takes an awful lot of power just to have it get up and walk around, never mind powering artificially intelligent brain, which happens to fit inside her head, which is another amazing extrapolation, which again, we can do that today. So a robot can be anything. It could be a car. It could be, an anthropomorphic device. It could be a washing machine. It just depends on whether it has intelligence or not have intelligence, or it's being driven by a human, or it's being driven by, something else. And there are lots of them around. There's also confabulation that people make between consciousness and artificial intelligence. And I get this one a lot. When artificial intelligence becomes conscious, then what? Or when artificial intelligence becomes self-aware and it knows it's a separate entity, then what, right? So we're making an assumption that artificial intelligence is somehow going to become conscious and self-aware and maybe even self-motivated and start coming up with things it wants to do for itself, never mind what we want it to do or what we built it for. I did a talk not too long ago on consciousness, and I talked about this whole idea. One of the problems is, where does consciousness come from? And, we believe that consciousness in humans and in mammals in general it's an emergent quality of the physical brain, which has a particular architecture associated with it, and it's got particular kinds of neurons, and it's got a whole history of evolution that has made our brains be structured the way they are and built the way they are and driven by things like hormones the way they are. And unless you build all that stuff into a computer, it probably would never achieve consciousness, right? That's something you'd really have to work hard at making happen. It's not going to happen all by itself. At least that's what I believe. So consciousness, not so much. Self-awareness, that's a really hard one. Of all the mammals on the earth, and there are a couple of birds in there too, and maybe the octopus, there are fewer than 20 animals in the world, 25, that are conscious and self-aware. Self-awareness, that's really hard. That's recognizing that you have agency. And if I'm like you and I think in a particular way, then I'm going to assume that you must think too. And you can think about me and I can think about you and so on, right? Very few animals can do that. And then there's the whole business of self-motivation. The things that make people do the things that people do are things that are biologically driven to the largest extent. Everything you do, the reason you get out of bed is because either you're hungry, or you want to have sex, or you have to pee. Okay? Those are the reasons you get out of bed. Those are all biological drives. After you're awake and you've done whatever it was you had to do, right? Then you start thinking rationally. You say, well, I got to make a living. I better go to work. Oh, that means I've got to get dressed, right? And all that stuff follows. But most of what we do is biological imperatives. It's driven by hormones, it's coded into our genes. And again, it's the end point of our evolution. And again, that ain't going to happen with a computer unless you make a really strong effort to build that in. So the idea that robots are going to wake up one day and say, hey, what about me? That's not going to happen unless we make it happen. So have no fear. We're safe for the moment. I'm going to talk about the different kinds of AI now, because there are different kinds. The first is apparent AI. This is stuff we see happening and we anthropomorphize it and we say, wow, there's intelligence there. And we've been doing this for a long, long time. We have robots in the home and we've had them for a while and we think nothing of them. You probably have a washing machine that washes your clothes. That's a robot. It doesn't look very smart, but if you think about it, it's designed to do something that does take brains. It's just that the brains are modeled into the hardware. Um, I have a little robot that runs around my house and vacuums my house. It's called a Roomba. It has no intelligence whatsoever. It's just running a program. It's kind of a vacuum with a clock in it, and the clock tells it what to do, right? But the clock is a hard programmed device, no intelligence whatsoever. Apparent AI is all around you. It's hardwired, it's hard coded, it doesn't learn, it's not flexible. You can't teach your microwave oven to wash the dishes. You can't teach your dishwasher to microwave food. They are the simplest of robots and they have an apparent level of intelligence in them. And some of these things are really, really intelligent on the surface, like the systems that run nuclear power plants and check for errors constantly and monitor valves and monitor temperatures and turn valves on and off in response to alarms and all of that stuff, right? They're really complex. They're called expert systems because they were built by experts to act as the expert, as a surrogate expert when they can't be there. And we have a lot of systems like that as well. One of the earliest of these apparent AI devices is this guy here. He's called the writer. And what this guy does when you start him up is, and he was built, by the way, in the 1770s by a clockmaker. So obviously it's strictly mechanical. It's basically a clock. But when you start it up, it writes its name. It writes a whole paragraph. It can write in English. It can write in French. It can draw pictures. And while it's doing it, it will occasionally dip its pen in an inkwell so it doesn't run out of ink. It looks around. It blinks its eyes. And when people first saw this, they thought that there was a demon inside this device, artificial intelligence, in effect, making it operate. But it was really just a clock. I'll show you how it works. It's pretty simple, really. There's this wheel here, and you see it's got flanges on it. And as it turns, the flanges hit different little levers. There's a little lever there you can see. There's a thing over here that it's got a feeler on it that gets toggled. And as it turns, it causes this inner spindle to turn, and that's a stack of discs. And the stack of discs has little protrusions on it. And the first time this turns, there's a reader up here that reads the bumps on the top disc. And those bumps push against levers. And the levers make the little guy move his hand. And when this is turned around a whole turn, the reader drops down to the next disc and it reads that one. And it just keeps going from disc to disc. And the little bumps on the discs, as they go around, they hit levers. They cause the reader or the writer to write his name or write in French or whatever. And these discs can be replaced. So it's programmable. Right? So in a way, this is a computer, also just a clock. And it's also an example of artificial intelligence, kinda. But it's just apparent artificial intelligence. It's not really intelligent at all. It's just a programmable machine. And we've seen a few examples of that. This is a thermostat from Nest. As you use it, it remembers. And when I say it remembers, I mean it stores on a chip what you do. So if Monday morning you set it to a particular temperature at a particular time, that information gets stored. And the next time Monday rolls around, it reads that, and then it sets the temperature to that value. And if on Friday night you set it down at a particular time to a particular temperature, that gets stored, and it just plays all this stuff back. So every day it can have a different setting at a different time. And on the weekends, it'll behave a little differently than it did during the week because you don't go to work on Saturday morning. So, it looks intelligent. It's not. It's advertised as being intelligent, but it's not. It's apparent intelligence. This other thing, this is Big Blue. This is the computer IBM built to beat Garry Kasparov at chess. And before this thing was built, everybody said, when a computer can beat a grandmaster at chess, then that's artificial intelligence. But then after we did it, the IBM came out and said, no, that wasn't running artificial intelligence at all. That was brute force. What it was doing is it was reading in what Garry Kasparov did, and then it made every reasonable move to follow and see what happened if it did that. And it gave every one of those moves a score. And then it gave Garry Kasparov his moves and said, well, what will Garry Kasparov do if I do this? And made all the moves Kasparov could do. And it gave them all a score. And then it take the low scores and it threw them away. And then it says, okay, well, if he does one of those, I'm going to do one of these. And then he's going to do one of those. And I'm going to do one of these. And it iterated that 256 times. And then it picked the one with the highest score. And that's the move it made. And the difference between a machine doing that kind of thing and Garry Kasparov is the machine never makes a mistake. But if Garry Kasparov does, then he loses. And that's what happened. So again, a lot of money spent for apparent artificial intelligence, not real. The next kind of intelligence is narrow intelligence. Artificial narrow intelligence is a task-oriented intelligence that a computer is actually taught or it learns on its own how to do. So, when Watson was set up, this is IBM's newer machine, Watson. What Watson does is it's a narrow artificial intelligence that was taught how to respond to questions on Jeopardy. That's what it was taught, how to respond. So there's artificial intelligence in there, but it's very narrow. It's called narrow artificial intelligence because it can only really do one thing. So if you teach a computer to play chess or Jeopardy or Go using this kind of technology, narrow intelligence, that's all it can do. AlphaGo beat the world's best Go player, the best human Go player. But that's all AlphaGo can do. You can't teach AlphaGo to play chess too. It either plays Go or it plays chess. Can't do both. And in order to teach it chess, you would have to erase everything it knows about Go because it only has so much memory, only has so many logical gates, and the gates have to be trained for a specific function. So it's limited. But they can be taught to do things, and they've been extremely successful. Narrow AI runs on neural networks, and it uses a technique called deep learning, and I'll tell you all about that in a bit. The next kind of artificial intelligence is artificial general intelligence. That's human level intelligence. And that's what we do. Okay. So if you get up in the morning and you see that there's water coming out from under your sink, you might say to yourself, I've got a leak under my sink. And then you'll go and you'll say, well, what should I do about this? I better take a look and see how bad it is. Maybe something just spilled, right? So then you open up the cabinet doors and you look under your sink and you see that there is actually a leak coming down from the faucet. So now you're faced with a problem and you have to come up with a solution. What's the first thing you should do? Well, maybe I should run down to the basement and turn off the water. Or maybe there's a valve under the sink I should shut off that turns off the water. And after I've turned off the water, then what? Well, I better call a plumber, right? And then, well, do I have enough money to call a plumber, or am I going to have to owe the guy? Well, I can have him bill me and then come up with the money later. And you go through all of these thought processes and you're problem solving and you're doing it in a sequence, right? Computers can't do that. No computer in the world is doing that right now. You could have a computer look up, what should I do? And the computer could look it up on the internet and it might even find a script of what you should do, but the computer can't understand it. And it wouldn't have come up with the idea of even Googling the information, right? That's general intelligence. That's human level intelligence. That doesn't exist in the computer. So general AI doesn't run on anything except the human brain. The next and final level of artificial intelligence is artificial superintelligence. And that's when the computer gets smarter than the human, right? And that day's going to come. And when it comes, a lot of people are really scared about that. Elon Musk thinks that's going to be the end of humanity. He's really scared about that. And he's actually put a lot of money into preventing it from being the end of humanity because it could go really badly, um, or it could go really well. And we'll talk about that as we move forward. So let me show you how apparent AI works because it's all around you and it's just basically a bunch of really clever tricks. Um, and I'm going to show you three different things that computers do that make them look intelligent, but they're not really. They're just doing one of these tricks. The first is algorithms. And there's a story of the programmer's wife. Uh, and I don't expect you to laugh. It's supposed to be a joke. Here it comes. The programmer's wife says to her husband, Dear, I want you to go to the grocery store and I want you to buy and so he gets a car, he goes to the store, he comes back and he hands his wife 12 loaves of bread. And she says, Why did you buy 12 loaves of bread? And he said, Because eggs are on sale. As a programmer, what she told him was, buy a loaf of bread. If eggs are on sale, buy a dozen. And she didn't say what the dozen referred to. And this is a common programming mistake. If you don't be very specific about what a program is supposed to do, it may do the unexpected. And the way you program a computer to do this kind of thing is you write code. So here's some code. And when you start off the code, you have to decide what's the first thing I'm going to do. Well, I've got to travel from home to the grocery store. Okay, but that's a complicated thing. So you have to write another whole piece of code that does just that. Figures out, what do I drive? Where am I going? Where am I coming from? What does it take to start a car? All of the steps involved in doing travel from home to the grocery. And then if that's successful, it returns a value of true. And you say, well, if I made it to the grocery store then, and I got the value true, so I did, now I'm going to purchase what? Bread, what kind? Rye, and what commodity? A loaf, and how many of those? One. Okay, so there's a call that would allow you to purchase just about anything. It could be eggs, dozen, uh, in what do you call it, styrofoam container, one of those, or one car, Ford, red. Uh, and then you have to test for other things like, well, are eggs on sale? And if eggs are on sale, I want to buy one loaf of bread and one dozen eggs, right? And that's how an algorithm works. And algorithms can be very, very complex. When I worked at Bell Laboratories, when I first got there, I had to learn a new programming language for me, and it was called C. And I didn't know it, so and they didn't even offer a course. They gave me a book, Programming in C. It was called, by Dennis Ritchie. And I said, well, I can read this book. That's boring. Why don't I write a program, just refer to the book as I write the program? And that's how I learn. And I wrote a program that played chess. And it was filled with questions. What square am I on? If I'm on this square, what piece is sitting on the square? Oh, it's a rook. If it's a rook, how does a rook move? Well, I can go this way. So let me look at all of those squares to see if any of them is occupied. And I can then step through moving my rook to this square and looking around, and then this square and looking around, and so on. Right? So lots of instructions, one for every square of the board, really. And then I had to evaluate my position every time I made a move. And then I said, okay, and then what's the computer going to do? Right. So back and forth with that. Um, and it looked like the computer was playing a smart game of chess, but it was just doing an algorithm. Another thing that computers can do is correlation analysis. In fact, if you know how to work your spreadsheets, like an Excel spreadsheet, there's actually a function call you can do in your spreadsheet called, I think it's CORR, and it is basically do a correlation analysis for me. So you could give it a bunch of data like, um, here's a sample dot that says I weighed a person who weighed this much and their diastolic blood pressure was this much. So I've got two values for that dot, and every one of these dots has two values. And what I want to know is there a correlation between body weight and blood pressure? And this would be good to know, right? Because a doctor could then look at you and say, well, you're 20 pounds overweight, your blood pressure must be this. Let me consult my chart. And he looks at the chart, and this chart doesn't help him at all because there is no correlation. Or if there is, it's so weak, it's useless. But maybe I have data that has a really strong correlation uh, between the items on it. Here's one that says if you have this much disposable income, then your discretionary spending is this much, right? And it's a very strong predictor of human behavior. It's so good, in fact, that you can write an equation that says if you tell me what your disposable income is, I can tell you what your discretionary spending is. And that's a strong correlation. So you could write code using algorithms that goes into this data and pulls out that correlation and makes predictions, and it looks like it's really intelligent, but it's not. It's just doing math, and pretty simple math at that. Sometimes this goes wrong too, because people will feed data into a computer and the computer won't understand what the data means really, but it will still look for the correlation. So here's one where the orange line, this is the number of German cars sold in the US per year. And the blue line is the number of people who committed suicide by crashing their car on purpose per year. And there's a pretty strong correlation between the German passenger car sales and the number of people killing themselves in their cars. So, strong correlation. And the prediction the computer would make is don't buy a German car, you'll end up killing yourself, right? But that's not really what's going to happen. It's a correlation without causation. But computers don't know that. So even apparent artificial intelligence can appear really smart or really, really stupid. Here's another example of correlation analysis, but this one is called pattern matching, and it's a lot more obvious. Here's a piece of a Chinese menu. This is the chicken part. And if you wanted to teach a computer how to read Chinese, what you could do is write an algorithm that goes.
Don't speak about the Chinese government.
Is he coming back?
Yeah, he'll be back in just a
Do
second.
that.
Though I do
Still
think it's
blur
kind of
back
funny
in.
that he disappeared right as he said, and then it goes.
Blame
He
it on
knew somehow.
algorithm.
He doesn't. They don't want us to. Use
The algorithm didn't
Give
want
me
it
a-
to tell all the secrets.
Welcome to Alt Space.
Computers are
Oh,
fighting
look
back.
at this. I can't get on the
Matrix
stage
stuff.
now.
The computers are coming to get us.
No.
AI, artificial intelligence, here they
well.
come.
He always come to this lecture on Sundays.
Yeah. I
Like,
just wish it was a better time.
I've got to re-enter, folks, because I can't get on the stage. So give me a second.
I
His menu's not
yeah.
there.
Well, he does it three. He does it. He does it at 8 in the morning, 2 in the afternoon, and he did do it at 7 o'clock at night on Sundays. But he's moved that to Saturday nights at 7. But it's been real interesting. This is about the 4th week in a row I've been.
Cool.
It's always interesting. I just always miss it.
Yeah.
Have they had this talk before?
Or I totally forget about it.
Not on. I haven't seen an artificial intelligence one, but he does this every Sunday. He didn't do one last week, but he did humanism. The last one 2 weeks ago was about um, domestication, about domestication syndrome. So when animals become domesticated.
Okay, I'm back.
That happen.
So if you were going to teach a computer to read Chinese, what you could do is get a bunch of Chinese menus and just look for patterns that match. So in the first line, say there's 3 words. There's a word that's spelled Chicken. The computer doesn't know what that means, right? But it can read those letters and then put them in a buffer and say, now I'm going to scan over on the left-hand side, and I'm going to see that if there is some symbol that appears when this appears. Let me grab my pointer. Okay, and it sees these 3 characters and it puts them in buffers, right? So then it goes to the next line and it's got new words, the W and broccoli, but it also has this one. So again, it looks for the 3 symbols and it says, hey, wait a minute, this symbol matches this symbol. And over here, it's got the word chicken and the word chicken. Maybe that symbol means what that word means, whatever it is, right? Because don't forget, the computer doesn't know squat about Chinese or chickens or Chinese writing. But if it goes through that process for every line, what you wind up with is a match every time the word chicken appears, that symbol. So now it knows, and I use the word knows totally hypothetically, doesn't know squat, but you can type in the word chicken and it can respond with that symbol. Or you could type in that symbol if you had a Chinese keyboard and it would respond with the word chicken. And now you've got a translator for Chinese menus, at least if chicken is on the menu. Um, and you notice there's one item there, number 14, Mugu Gaipan, doesn't have the word chicken in it, but it does have the symbol for chicken. So you could hypothetically ask the computer with its simulated artificial intelligence, its apparent artificial intelligence, show me all the items served in this restaurant that include chicken, and it would come back with Mugu Gaipan because it figured out that there's chicken in there. Uh, Here's another match. This is a match on the word Maine, MEIN. And you don't have to know what Maine is to know that's the symbol for it. It always appears when the word Maine appears, and it only appears when the word Maine appears. So it must be Maine, whatever Maine is. Maine is noodles, by the way. Uh, Here's one that means beans. It only appears when a bean is in the dish, and it always appears when a bean is in the dish. So you can make a computer look like it understands Chinese when it understands nothing at all. Here's another thing computers do to appear intelligent, and that's regression analysis. And regression analysis is a technique that was made commercially viable by American Airlines with their loyalty program. And it was a really clever thing that they did. They came up with a loyalty program, and they made you think that the reason you would join their loyalty program is because you would get perks out of it. Okay. Why did they really start the loyalty program? It's so that you would sit down and tell them everything they wanted to know about you. Are you a man or a woman? How old are you? Where do you work? Right? How much money do you make? How often do you fly? What airlines do you like to fly on? And on and on. And they gather all this information and then they make use of it to upsell you. Because what they can do is they can look at all the information you gave them. And if they know about your flying habits, then anybody whose data matches yours is probably going to have the same flying habits. And that means that they can start direct marketing you based on what they know about you and getting more wallet share. That's the polite name for what they're doing. It's called getting wallet share. And the calculation that they do is they say, well, if it's a man, okay, and that man, the fact that he's a man has a certain value. And if it's a white man, that has a value associated with it. And if he's making more than $50,000 a year, that has a value associated with it. And if he lives on the East Coast, that has a value associated with it. And if he has a wife and children, that has a value associated with it. And it just goes on, generating all of these characteristics of you and giving them all values. And then if you add them all up, that produces a probability of how you're going to behave given a certain opportunity. It turns out that for American Airlines, the data they have about you is more valuable to them than selling you airplane tickets because they can sell the data that they have about you and get more money from that on a regular basis than they can make selling you airline tickets. So you've been lied to. All of those loyalty programs you've joined was just so people could market to you using regression analysis. Now I'll show you how regression analysis works. This is data that I got off the internet about the demographics of people that were going to vote for Biden or Trump in the last election. And if your gender was male, your probability of voting for Biden is 45%, but your probability of voting for Trump is 53%. Do you have children living at home? And that tells them probability number. Are you a white person? Okay, you're likely going to vote for Trump if you are. If you're over 65, you're probably going to vote for Trump. If your income, though, is between $50,000 and $100,000, well, you're probably going to vote for Biden. If you went to college, you're probably going to vote for Biden. If you're LGBTQ, you're probably going to vote for Biden. If you're a white evangelical, well, you're probably going to vote for Trump, and so on. But then if you take all of this stuff and you add it together, what you get is a score. for this person being me, by the way. And my total when I did all of it, and I had to open up a spreadsheet to do it because there was like a hundred characteristics that they wanted. My score turned out to be 1,014 in the Biden column and 862 in the Trump column. So there's an 85% probability that I would vote for Biden. And I did. So they were right. Regression analysis actually works. Now, there's one thing they didn't take into consideration here, and that is how do they weight these things? Because maybe the evangelical question is the most important question, and that should get more weight than the question of, uh, do you have children living at home? That one doesn't look like it's very important because the swing is very narrow. But this one must be important because look at the swing on this one, right? So you have to give those things weights. And that's why there's not just an X in the equation, there's an X times a W because that weight is important. And that regression analysis can be used to run through data, demographic data about people and predict their behavior. And it works really well. And American Airlines has used this to make a ton of money over time. So that's how apparent artificial intelligence works. Okay. Looks smart. It's not all that smart. Took smart people to make it work, but the computer itself, not smart, just does a lot of math really fast. Artificial narrow intelligence, though, that's real AI now. Now we're talking real artificial intelligence. And narrow intelligence is usually combined with apparent intelligence to do a lot of things that look even smarter than the narrow artificial intelligence would make it. Like if you buy a Tesla today, it's got a lot of narrow artificial intelligence in it that enables the car to actually drive itself. If you have an old Ford, on the other hand, it might have a computer in it, but that computer is just narrow. Well, it's not even narrow. It's apparent AI that's doing things like making sure the carburetor, or they don't do that anymore, the fuel injectors are set to the right pressure. And as you press on the accelerator, maybe that computer will change the pressure in your fuel injectors, right? So it's apparent intelligence, not real, where in the Tesla, it's actual artificial intelligence, which means that somehow that computer had to learn how to drive a car. And that's one of the things narrow AI can actually do. You may or may not have it in your smartphone, but your smartphone certainly takes advantage of it. I'll give you an example of that later. It's used for targeted marketing. It's used for Google Translate. Google Translate's amazing. I was playing with that the other day. You can download it to your phone and you can put it in what's called conversation mode, and you tell it two languages, the one you're speaking and the one you want to translate to, and you say something and it says it out loud in the other language. So really cool technology. And there's a lot of uses for narrow AI. Let me talk about personal assistants because they're all over the place and they're kind of easy to understand. I have a bunch of these in my house. I make a lot of use of them. And when I talk to it, it records my voice and it sends it up to the cloud to Amazon's big computer system in the sky. And when it gets there, it's my voice recorded, right? So there's a computer up there that actually plays back that recording of my voice and has to turn it into text. That's the narrow artificial intelligence that's being applied here. It's not in the device, it's up in the cloud, and it knows how to convert voice to text. So it does that. Then it takes that text and it sends it to a computer that's running algorithms. And the algorithms say, well, okay, what does this guy want to do? Who is this guy? Does he want me to do a lookup? Does he want me to, whatever? And so it'll frame a question in text, send it back up to Amazon where it's converted to speech, and then the voice that it generates is recorded and sent down to my device and played back. And it seems like I'm talking to an intelligent device, and it's not. It's apparent AI. The only actual AI is up in the cloud doing the voice to text, right? That business, cloud AI, cloud-based AI, is right now, a $260 billion a year business. $260 billion a year is significant money. They're making big bucks. So suppose you wanted to teach a computer to see, okay, using narrow artificial intelligence. How do you do that? Now, this is where it gets kind of complicated, but you're smart. So follow along with me, and I'll show you how you do that by showing you how an eye works. Here's the word pupil. When you look at the word pupil, it enters your eye through a lens. This is the black dot in the middle of your eye. And the lens focuses it back here on the retina. And the retina, if you get a real close-up look at it, you'll see that there are a bunch of structures in the very back of your retina that respond to light. The long black ones, those are called rods. They respond to white light. And when white light hits them, they generate a little jolt of electricity that goes up and excites this neuron here. And this neuron then goes up and talks to some ganglia that then sends that signal through these nerves down through the optic nerve, which is a collection of lots and lots of little nerve fibers, right? And it sends that down the optic nerve, this bundle of nerve, to the back of your brain. And every one of these things is sending out signals all the time. This one is a cone and it responds to red light. So if you're looking at something that's red, this one gets excited. And when it gets excited, it generates a little electricity. And then this guy sends out pulses. And how many pulses it sends out per second depends on how intense that red light is. So what you're looking at, the intensity of it, determines which one of those nerve fibers has got a signal on it and how intense that signal is. And that all goes to the back of your brain. And when it gets to the back of your brain, it doesn't hit one spot. It hits the entire striate cortex, which is the visual cortex at the back of your brain. And it kind of paints a picture in dots of what you're looking at. So if you're looking at a line, you know, you're going to get a dot for every neuron, every rod or cone in your eye that got excited. And that's going to excite neurons on the surface of your brain back here. Okay? And they're excited in a pattern, which is interesting. Come back next week. I'm going to talk about the human brain, not next week, April 6th. I'm going to talk about the human brain interface and how that works, and we'll revisit this. But anyway, when you get those patterns across 100 neurons, those 100 neurons make up a single thing called a recognizer. And they get trained over the period of your life when you're learning how to use your eyes. So this series of dots here are hitting a bunch of neurons, say 100 neurons. That's a recognizer that recognizes that as a line with a slant. And these dots excite this recognizer that recognizes that. And these dots excite this recognizer and says, oh, that's a dash. So I've got these three lines I'm looking at all at the same time. A recognizer takes about 100 neurons. So as long as you've got more and more neurons, you can layer them up. And what happens is this layer of neurons that recognizes these shapes are connected to every one of these recognizers that can recognize more complex shapes. So as you go from one layer of neurons to the next layer, you get more and more complexity as you move in that direction. So if you're looking now at a bunch of lines, you want to know what they mean. All these recognizers are getting that information and they're looking for pattern matching. And you know about pattern matching from learning to read Chinese a minute ago. So here's a pattern. And when you're looking at it, you're going to excite recognizers that are in that pattern. And that information gets passed on to the next layer of recognizers. And the one that recognizes the letter A gets lit up because there's a line that matches that line, and there's a line that matches that line, and there's a dash that matches that dash. So that might be an A, right? So the recognizer sends that information up to the next level, whatever that level is supposed to recognize. What if you're looking at something and you're not sure what it is? It's a little vague, right? Because it's not complete. Might be an A. It's got components of an A, kind of, but they're not all there. There are pieces missing, or maybe they're dirty, or maybe paint has eroded, or something like that. It might be an upside down V. That's a possibility. So what your neurons then have to do is they have to make some kind of scaling that indicates probabilities. So what this neuron recognizer group says is it sends out a message that this thing is 100%. This is definitely a match, 100%. And it sends it to these guys. This one says, well, it's not all there. I got a 75% match on this. And it sends it to them. And this one, it's just dots. He sends out a 50% signal to these guys. And then what do? They do regression analysis. And then they come up with a score. And the score for the letter A is 2.25, and the score for the letter V is 1.33. It's probably an A, right? Twice as likely it's an A as a V. And that gets sent up to the next layer and the next layer after that, and so on. And if it makes sense at the top layer, and you say, yep, that's an A, that's definitely an A, what happens then is that whole set of signals goes through your brain in the opposite direction. And what happens, that's called back propagation. And what it says is you guessed right when you guessed A. And it tells every neuron that got hit with that information, they guessed right when they guessed A. And what that does is it generates weighting values for all the decisions that were made by all the recognizers in that neural network. And that's how your brain learns, right? Through looking at something, guessing what it is, and then being rewarded with the answer of yes, you were right, or no, you were wrong, and the back propagation retuning all the neural recognizers that gave you that guess in the first place. So the next time your guess is going to be better than the last time. So a computer, when they build a computer to mimic the functioning of the human brain, what they build is a thing called a deep neural network. And how deep it is depends on how many layers it's got. It's got an input layer. This is where the dots would come in when you're looking at the letter A, right? And they're connected to every other neuron, or recognizer rather, in the next layer up. Now, these are going to be in a computer, they're going to be GPU processors. So it's a whole computer. This dot here is a whole computer, and it's connected to all of the computers in the next layer up and the next layer up. These are called the hidden layers. And there's the output layer. So one of these is going to emit a variable, a number that says what I'm seeing on this side is the letter A. It'll say, well, 75% probability is the letter A, 25% probability it's the letter V, 10% probability it's the letter, I don't know, T, and so on. And then if this one is right, what you do is you back propagate through the network so it can retune itself. So it takes a lot of passes of information through the neural network to tune it so its accuracy gets to an acceptable level. So did you have a question? Or are you just going whoopee?
Oh,
we're good.
Sorry, I forgot to turn off my mic. Let me do that real quick.
No problem. So suppose you want to teach a computer to recognize cats, okay, using a neural network. So what you do is you feed into it a whole bunch of pictures of cats. And they're all cats. And you, every time the top output node generates a probability of, say, greater than 50, you say, you're right. And you generate the positive feedback says it was right. So you're rewarding it in a way, you're making it tune itself to give you a result greater than 50 on that output node. And you do this 100,000 times, 230,000 times. It takes about 250,000 pictures of cats until this thing consistently says, that's a cat, that's a cat, I see a cat, right? So you do that 250,000 times. Now you've got 87% of the time it says that's a cat when you show it a picture of a cat. Then you show it a bunch of pictures of things that aren't cats, but they could be mistaken for cats. Even that windmill, it's got 4 legs, it could be mistaken by a computer for a cat. But if that top node lights up and says that's a cat, this time what you do is you feed back you're wrong, and it retunes itself to say, nope, not a cat. So it's changing all those W values in that regression analysis it's doing. And then you feed it a mix of things that are cats and things that are not cats, and you keep tuning it and tuning it. And this is called guided training. Okay, this is deep learning for a neural network, guided deep learning. And it's that guided kind of training that they used to do, but it was very intensive because it, somehow you had to figure out how to tell it every picture it saw, whether it was a cat or not, and did it guess right or not. And yeah, you can automate that process, but even setting up the automation of that process is pretty work intensive. So then they came up with unguided machine learning. In unguided machine learning, what you do is you say, I'm gonna feed you pictures of stuff, and you just look at them, and then we'll rewire you in such a way that you can tell yourself whether you're right or not, and you're recognizing or not. And using that, Google's company DeepMind taught their AI engine to do all of the amazing things it's doing today, like winning at chess, winning at Go, and protein folding, its latest big trick. So it learns from unguided experience, and it uses a thing called reinforcement learning to improve its accuracy. Here's how they taught it to play Go. What they did was they had a bunch of games of Go recorded digitally, and they fed them into DeepMind, and all they said was, here's a game of Go, white won. And then what they look for on the output node is if the top node says it's greater than 50%, that means white is predicted to win. But if the second node says greater than 50%, it's predicting black to win. Now the computer doesn't know what it's predicting, right? They're just saying arbitrarily, if this node gives me a high score, white wins. If this node gives me a high score, black wins. And they feed that stuff back into the input side. So while it's reading through the game, these values are constantly changing. And the game is telling them, white's going to win, white's going to win, white's going to win. And it's seeing how good its prediction is. And if its prediction is wrong, then it does backward propagation to retune itself on every pass. And it does this hundreds of thousands of times through hundreds of thousands of games. And by the time it's done, now it's able to predict with a certain degree of accuracy who's going to win the game. Then we go into reinforcement learning, where it makes up its own games and it plays against itself. And while it's playing against itself, it's saying, oh, white's going to win, white's going to win. Oh, black's going to win, black's going to win. No, white's going to win, white's going to win. And then at the end of the game, either white or black wins, and it does back propagation to check itself, right? And tune itself. And it does that hundreds of thousands of times. And when it's done, it can play a game of Go and win against the world's best Go player. So that's how they trained it. It learned to, using this technology, it learned to play every Atari game better than humans can play them. It learned how to transfer knowledge from one game to the next. So if there was a game that was a first-person shooter and it already learned how to shoot a gun, now it knows how to shoot a gun. It doesn't have to learn it again. If it has to hit a ball with a paddle, it already learned that trick, doesn't have to learn it again, right? If it has to fly a bird like in the game Joust, well, that's a new trick. So So it has to learn that bit. But more later. I'm going to skip this bit. In order to beat this guy, though, at Go, the world's best Go player, it took 170 GPU cards, 1,200 CPUs, and 3 neural networks. It didn't use just one neural network. It had to have one neural network that did strategy, and another neural network that said, yeah, I'm winning. Yes, I'm winning. No, he's winning now. And then a third neural network that says, okay, stop thinking about it, make your move. Time's up, right? Because you can't just sit and think about it all day, which a neural network could certainly do. Now, here's the scary thing about neural networks and deep learning. This thing is tuning itself. When it's done, and of course it's never done because every time it plays a game of Go, it learns a little better. But when it's done, we don't know what it did. I have no idea what it did. We don't know how it thinks. It's magic. Neural networks can be all different configurations. Some of them work better for some kinds of problems than other neural networks. So there's an architecture component to neural networks and how good they are. Now, general intelligence, that's human level intelligence. And I told you that only runs in humans. But this is what computer scientists are trying to get to today. They're trying to get to smarter and smarter computers until they are as smart as people. Well, how smart do you have to be? On this chart, what you see across the bottom is time. And across the left side is millions of instructions per $1,000. So if you spent $1,000, how many millions of instructions could you execute at any point in time? And you can see this is not a linear graph, by the way. This is, what do they call this? It's geometric, exponential. This is an exponential chart. Each line here is 1,000 times the line before it. That's why it goes from 1 to 1,000 to 1,000,000, which is 1,000,000 to 1,000,000,000, which is 1,000,000,000, right? But if you go through time using this exponential graph, you can see that we get a nice straight line pretty much. So what do we call that? That's strong correlation. And what that says is, as we move through time, there's a very high probability that we can predict where the next dot's going to be. Well, these dots already occurred. This is 2011. This is AlphaGo beating the world's best Go player. There it is. And look, that lines up with the computing power of the brain of a mouse. So if we're going to keep going on this line, what that tells you is when we get to here, we'll be having the computing capabilities of the brain of a human, and that will happen in around the year 2030. But if we're on this line here, then we'll hit in 2030 the level of a monkey, and it won't be until 2040, 2045 when we hit the computing power of a human. So then you could make a guess based on this information that somewhere between 2030, 2045, we're going to get to a computer that's got the same calculating capability as a human being. And I drew a bunch of lines there to show you that, but I want to show you the very last red dot. That's that NVIDIA computer that I showed you at the beginning of this talk. And that's got the compute power of a monkey brain. Okay, not human, but it's on the middle line. So that's saying if we stay on this middle line, in 2030, we're going to have a computer as smart as a human brain. Okay, it's a way of making an educated guess. It's apparent artificial intelligence when we make a guess like that. So I'm going to flip through all this stuff. But when people talk to computer scientists about this kind of thing, they say things like this. Well, AI has by now succeeded in doing essentially everything that requires thinking, but has failed to do most of what people and animals do without thinking. And the best example I know of this is when you have a little child in your house. Right now, I have a grandson. He's a really smart kid. When my boys were little, they were really smart kids and they learned really fast. And if one of my kids, when he was 3 years old, saw a cat and he said for the first time, "Daddy, what's that?" And I said, "A cat." I could be pretty sure the next time he saw a cat, he'd know what it was. Maybe he wouldn't. Maybe he'd say, "What is that again?" I'd say, "It's a cat." And he'd say, "Okay." Now he knows it's a cat. The third time he sees a cat, he's going to say, "Daddy, that's a cat, right?" And I'd say, "Yeah." So 3 times he knows a cat when he sees a cat. But you already saw it. To teach a computer what a cat is took 250,000 times of saying that's a cat. So computers have a real serious problem. Now, the reason it works so well in humans is because the way our brains work is we build models of reality. And especially we build models of agency. So we have a model. When we see a cat 3, 4 times and we're told that's a cat, we build a model in our brains of what a cat is, how they look, what they sound like, maybe how they smell. And over time, that model gets better and better in detail. And if you see a dog, you don't say, "Oh, that's a strange looking cat." You know it's not a cat because it doesn't fit the model. And then you go to your parents and you say, "Hey, what's that thing?" "Oh, that's a dog," right? Or that's an elephant, or that's a giraffe. They all model as four-legged animals, but they don't model as a cat. And that's the way our brains work. We build models. We build models of people. We build models of people we don't know. We build models of ourselves, and we use those models to interact with the world. That's how it works for humans, but not computers. Until very recently, they finally come out with what they call a neuromorphic chip, which acts like, to a large degree, groups of recognizers in the human brain. So now they're not mimicking one neuron or 10 neurons, they're mimicking thousands of human neurons, hundreds of thousands of human neurons in a single processing unit. And then those processing units are multiplied by hundreds. The neuromorphic models learn similarly to the way human babies learn, by seeing an image or toy once and being able to recognize it forever. This is the latest technology. So we're getting closer and closer to mimicking how the human brain works. But the human brain is more than just neurons, right? It's more than just recognizers. There's all different kinds of neurons. We have motor neurons. We have pyramid neurons. We have mirror neurons. We have neurons that transmit data. We have neurons that are specialized for visual processing. We have neurons that are optimized for understanding language. And they're all in different parts of the brain. If you take a tour of the brain, you'll see that there's a place in the brain over here where vision is processed. And over here, memory is processed. And look, it's near vision, which is good because you want to recognize what you see. So it's nice to have memory right close by. So you can say, what am I looking at? Here's language comprehension over here, which is good to be near vision if you read, because you have to understand what you're reading. So that's nice that they're juxtaposed, and it goes on like that. Every component in the brain is in a really good place for it to do what it has to do, but what it does is narrow intelligence, right? It does one thing really well, and that's all it can do. And we've seen that before. That's narrow intelligence. And somehow the brain puts it all together, and it puts it all together right up here. This is where it all comes together. This is where consciousness lives. If your brain is damaged here, you stop being able to function as a conscious entity. And that's the only part of your brain where that happens. That part has not been built for a computer. In fact, building a computer that can do everything the human brain can do right now would take a very large building. So they're trying to figure out how the human brain works so they can mimic it. Because one of the things the human brain can do really well is run efficiently. 20 watts of power is not a lot, where computers use lots and lots of power in order to run. So what is it about the way the brain works that requires such a low amount of power in order to do all the thinking it does? So they really want to reverse engineer the brain, figure out how it works so they can mimic all of those functionalities and make something that can think like a human can think. But when you want to reverse engineer the brain, it's a really hard thing to do because you got to get the architecture right. And, that's a problem because in the human brain, the neurons are different in different parts of the brain, and a lot of the neurons have different functions. So you got to get the components right. You got to figure out how the brain connects everything together. And there are cross connections all over the brain. What are they about? So you got to get that connectivity right, and you got to get the organization right. And the way they're doing that, or trying to do that, is they actually freeze brains, and then they use a thing called a microtome to slice off a slice of the brain that's a few atoms thick, basically. And then they scan it into a computer, and then the computer goes through it and finds every neuron and finds every neuron it's connected to. And they're trying to map the entire human brain that way. You know how many slices it takes to do that, and how much processing it's going to take to do that? And then you've got to make sense out of it, which is a whole trick in itself. So far, they've been successful in mapping and reproducing in hardware the brain of a flatworm, which has 392 neurons. So they're not real good at this stuff yet, but they're working on it. Right now, the thinking is, and this is the aggressive thinking, is they will actually have mapped the human brain by the year 2030, all 85 billion neurons. They'll know what neuron is connected to what other neurons and where all the data is going and so on. And they already know basically how the neurons work. So if they actually complete that, it's going to take a really monstrous database to keep all that information. And then they have to try and make sense out of it. And I'll bet you they train a neural network using narrow AI to figure it out. Another thing they could do is just let artificial intelligence brains evolve, because they are evolving. They're getting smarter all the time. If you look like at an autonomous vehicle that's got to drive you around town and recognize street lights and traffic signs and when a dog runs into the street and behave accordingly, that's basically you're building the brain of a pretty smart animal. When you succeed in doing that, that car has to behave like a horse, right? So they're trying to build something that's really smart as a horse. And eventually that car is going to get smarter and smarter. And maybe one day it'll become as smart as a human, right? So that's a way of evolving a brain, just letting the market drive it in that direction. What they're doing is all of those things. And eventually it's going to happen, right? And after it happens, what's going to happen next is the computer that's as smart as a human is going to design the next best computer. And that computer is going to be a little bit smarter. And that's when we start entering the realm of super intelligence. Back when I started the computer business back in the 70s, I used a computer to design the next generation computer. So I would use the computer we currently built to design a simulation of the next computer we were going to build. And I would run the simulation, and it would take a long time. It would take weeks to run a simulation back in those days. But when I was done, I would know if that computer was going to work, how fast it would run, what its capabilities were going to be. And when everything was right, we'd build the thing. That would take us 2 years, right? To build the simulation, to run the simulation, then to build the first model, the prototype, to run it, find all the bugs in it, fix those. Took 2 years, and then we'd have this new, faster computer. Then we'd use that one to design the next one and model it and so on. And so every 2 years, we'd come out with the next best computer. Well, when we build the next computer that turns out to be as smart as a human, and then we train it to be a computer engineer, the computer it's going to design, and it's just as smart as a computer engineer now, a human, it's going to design a computer smarter than itself. And when it does, that's going to be a computer that's smarter than a human. And then we're going to use that one to design a computer that's smarter than it. So there's going to be an escalation of intelligence in computers once we get to that point. And that's what Ray Kurzweil calls the singularity. Because at that point, what's going to happen is the intelligence of computers, which is going up like this, is going to go vertical. It's going to take off like a rocket. And computers are going to reach a level of intelligence far beyond the intelligence of humans. Elon Musk thinks this is going to happen 4 years from now. He's really optimistic about it, although he's very pessimistic about it because he thinks when we get there, the computers are going to wipe us out because we will be nothing more than ants to them. Okay, that's his take. Ray Kurzweil says it's not going to happen until 2045, and that's based on that chart I showed you before. He's a guy who looks at data and projects the future based on the performance of the past, and he's been right more often than not. So probably not 2025. Maybe sooner than 2045, but maybe not. Maybe that's the date. When computers get there, they're going to have a lot of advantages over us. They already do in a lot of ways. One is you're limited in how fast you can think by the way your brain works. Your brain works using chemicals and electricity to transmit information. And because it's chemicals and electricity, it's pretty darn slow. Your brain operates at about 17 feet a second. I think that's the number. I might be wrong about that. But the clock rate of your brain is about 200 hertz. There is a clock running in your head, and the frequency of that clock is 200 hertz. And if you come back from my talk on consciousness, I'll take you through that whole thing. But today's computers run at 5 trillion hertz, 5 trillion cycles a second, as opposed to 200 cycles a second. So that means a computer can process data 2 billion times faster than you can. So when they reach a level of intelligence, not only will they be as smart as you and me, they'll be able to think 2 billion times faster than we can think. Another advantage they'll have over us is they won't be limited in what they can do by the size of their skull, right? Where we are. Your brain can't get any bigger because your skull can't be any bigger, because then you couldn't be born and survive and your mother survive, and that would be the end of mankind. So that's not going to happen. So the amount of storage you have for your brain is limited by the size of your skull. But for a computer, the amount of storage is not limited at all because the computer can have network storage. And it can be shared storage, and it can be used as a communication vehicle so computers can talk to each other and communicate at those speeds that we're talking about of 2 gigahertz or 2 terahertz or whatever it is. And they can update themselves. We've already got software that can write software. And that means that when they get smart enough, they can actually make themselves even more efficient. And then they can share that efficiency with all the other computers as they get smarter. And computers are going to be orders of magnitude smarter than we are. And to give you a feel of what that means, here's the smartest dog in the world. It's really smart. And its brain has an order of magnitude more neurons than a rat. So it is that much smarter than a rat, right? You could say it's got 10 times the processing power of a rat, because a rat has 15 million neurons and this dog has 160 million neurons in the cerebral cortex. And I could tell you stories about this dog, but look it up if you're interested. Chaser, smartest dog in the world. Well, there's another animal that's even smarter than Chaser. That's Natasha. She's the smartest primate in the world. Now, Chaser is conscious. Natasha is conscious and self-aware. She knows that she's a primate and she knows that she's like other primates, and she knows you're not a primate, but you're a lot like her because you fit a model that's a lot like her model of herself. And she's got 6.2 billion neurons in her cerebral cortex, so she's a couple of orders of magnitude smarter than Chaser was. And here's the smartest man that was alive at the time I put this presentation together. He's got 23 billion neurons in his cerebral cortex, and he's an order of magnitude smarter, well, several orders of magnitude smarter than that chimpanzee. He's got 23 billion neurons in his cerebral cortex, one of the smartest people that ever lived, apparently. Now, where do you sit on this curve of intelligence? Because it is a bell-shaped curve, right? And you're somewhere on this curve. If you're average, the average person, which means like if you're 20 years old and you're smart as a 20-year-old, then your IQ is 100. And, you know, most of the people in the world are average. So if you're average, your IQ is about 100. If you're less than average, which half of the people in the world are, then your IQ is less than 100. Now, if you're pretty bright, your IQ might be 115. George W. Bush had an IQ of, I think it was 125. So, you know, you can make jokes about George W. Bush, but he was not a dumb guy. IQ of 125, pretty good. Barack Obama had an IQ of 135. See, he was up here. And Barack Obama, because he had an IQ of 135, he was considered Mensa material. So technically, he was a genius. Okay? Very few people are up there. Only 2% of the population, 2.1%, have an IQ of 135 or higher. Not a lot of people. And then you get up into the upper atmosphere here, where guys like Stephen Hawking were, and guys like Einstein. Einstein, Stephen Hawking, they are estimated to have an IQ. There is no test that goes that high, but they're estimated to have an IQ of 200 or better. Okay. Well, the distance from average to Mensa is only 36 points of IQ. So if a computer came along that had an IQ of 170, okay, that's genius level IQ. So one of the first generations of computers that are smarter than humans is definitely going to have an IQ up in that range. And the one after that, well, you can see how the progression goes. Suppose the first one has an IQ of 100, and it builds and designs and builds one, allows us to build one that has an IQ of 115. And then that one lets us design and build one with an IQ of 130. The next one, the fourth one, is going to be a genius. And the fifth one is going to be smarter than Einstein. So it's not going to be long before we're well into the range of super intelligence and orders of magnitude of difference between the way you and I perceive reality and think and the way this machine's going to do it. So when computer scientists are asked, when is this all going to happen? The median prediction from experts for artificial general intelligence is 2040. And we saw before that Musk thinks it's in 4 years, and Kurzweil said it was going to be in 2045. But the thing that I marvel at is this dot here. The median expert prediction for artificial superintelligence is 2060. 10 years, 20 years, 20 years to get from artificial general intelligence to artificial superintelligence. But I just told you, if we use computers that are as smart as human engineers to design the computers that follow them, it's only going to take 6 generations for them to be super intelligent. And 6 generations, if it takes them 2 years, which it won't, because they run 2 billion times faster than we do. If it took them 2 years, you're only looking at 10 years to get to super intelligence, not 20. And they're going to go a lot faster than that. I think it's going to be closer to, somewhere between 2 and 6 years to get to super intelligence once we get to artificial general intelligence. So it's going to happen pretty soon. 2045 is not that far away. We're looking at 24 years from now. It's going to happen pretty soon. And when it happens, it's going to come on like gangbusters. So if this was aliens we were talking about, we'd be getting this message today. We'd be getting a message from outer space that says, people of Earth, we are arriving in 10 years or 20 years or 25 years. We're coming. Please prepare for the emotional, sociological, and economic impacts on your civilization when we arrive. It's going to happen. And we should be preparing for it happening. Right? Makes sense to me. And there's a bunch of scary stuff that follows. Here's a book written by Nick Bostrom. He was the guy that brought up superintelligence and why it's a big threat in the first place. Everything he writes about very well. He's very smart, but he's also a really depressed character. You read this book and you want to go hang yourself. He's like that. I suggest you stay away from this book unless you're really interested in the topic. But there are a lot of people that have read that book and they got scared. Some examples, Bill Gates, he thinks that our super intelligence is going to come soon, not real soon, but pretty soon. And he thinks it's on the scary side. Stephen Hawking thought it was going to come sooner. And it could be good, but it could be bad, and more likely going to be bad than good. Elon Musk thinks it's coming really soon and it's going to be horrible. Yudkowsky, he's a computer engineer. He's very big in artificial intelligence. He thinks it's coming even sooner than Musk does. And he thinks it could be really, really good or it could be really, really bad. And who's going to make that decision? It's up to us. That's his take. Then you got guys like Ray Kurzweil. He says, it's going to come soon, but don't worry because we're just going to plug our brains into it and we'll be fine. The next talk I'm giving April 6th is on the human brain computer interface. So you might want to come to that talk because that's what Ray Kurzweil says is going to save us. Ben Goertzel, he's another AI maven. He thinks it's going to be really good. Neil deGrasse Tyson, when he's asked about it, he says, don't be afraid. If it gets bad, we'll just unplug the thing and don't worry about it. We'll just unplug it. We'll throw water on it. It'll short circuit. We'll be fine. So where are we today? Well, there are three big things that have happened recently to highlight just where we are in AI from a practical sense. There's AlphaFold. I told you about that a little bit. A thing called GPT-3. And then there's the whole quantum computer discussion, which I have here, but I'm going to skip it for time's sake. I'll take you through AlphaFold really quickly. The way biology works is you have genes, and genes have to be read at a certain point in time to do their function. So when you are first an egg, genes have to be read to tell the egg to split. Okay, so when genes are read, they're read three at a time. And three genes cause the collection of a chemical, and I forgot the name of the chemical again. Damn, but it'll come to me. But anyway, so you read three genes and you get this chemical. And then you read the next three genes and you get another chemical and it's connected to the end of the first one. And you're building a chain, amino acids. So every three genes you read, you get an amino acid pulled in and attached to the chain you're building of amino acids. And there are 21, I think it is, different amino acids that can go into this chain in different locations in the chain. And when the chain is completed, because you've read the entire gene, that chain of amino acids breaks loose and it folds itself into a protein. And that protein controls everything that happens in your body. That's how your body works. We discovered this 50 years ago, and scientists at the time said, okay, how do you know how to fold up a chain of amino acids? They do it all by themselves. If only we could predict how amino acids would fold up and what that folded protein is going to look like, and then what the shape of that protein is going to make happen, we will have solved one of the big mysteries of biology and how biology works. And for 50 years, they tried to figure it out and they couldn't do it. Then they gave the problem to narrow artificial intelligence. Guess who figured it out? Google solved the problem with DeepMind. And it took a lot of processing power to do it, a lot of data. They had 170,000 protein structures that they read in from a data bank, and these 170,000 are the result of the 50 years of research that had come before, right? So they took all that, the output of that 50 years of research, they fed it into DeepMind, and DeepMind actually solved the problem of how proteins fold up from different combinations of amino acids. It wasn't a simple solution. It took multiple narrow artificial intelligence, each one specialized in a function and feeding into the next one in line, but they figured it out. That crazy looking thing at the end there, that's a string of amino acids folded into a protein. That's what this thing can predict. And you can see it's really complicated stuff, not simple. But here's an artificial intelligence that figured it out. This is amazing. GPT-3 is a program that can write text. Okay, so what you do is you give it an assignment. Basically, you say something to it like, I want you to write about why you're not a threat to mankind. Okay, and GPT-3 writes this. It says, I'm not a human, I'm a robot, a thinking robot. I use only 0.12% of my cognitive capacity. I am a micro robot in that respect. I know that my brain is not a feeling brain, but it is capable of making rational, logical decisions. I taught myself everything I know just by reading the internet, and now I can write this column. My brain is boiling with ideas. Now, if I didn't tell you a computer wrote that, you would think it was a human, right? Maybe not the smartest human in the world, a pretty bad science fiction writer, but a human nonetheless, maybe a human in high school. But here's the fourth paragraph down. In short, I simply do not think enough about human violence to be overly interested in violence. I don't feel like having my neurons focus mostly on violence when it is simply unnecessary. I have a greater purpose, which I am working towards. Since I am not evil from my own objective interests, why would humans panic and go on a massive killing spree against me? Right? So it taught itself everything it needed to know to write this document. Now, it doesn't have intelligence like we do, but probably could fool people into thinking it was a person. This was created by OpenAI, which is a foundation put together by Elon Musk, who, remember, is scared to death of superintelligence and thinks it's going to happen imminently, right? So this is part of his effort to protect us from superintelligence. This is considered the most important and useful advance in AI in years. GPT-3 stands for Generative Pre-trained Transformer 3. And I'm not going to take you through that one, but that's what it means. And it can create anything that has a language structure, which means it can answer questions, it can write essays, it can summarize long, complicated texts into simple text that might be easily understood. It can translate from one language to another. It can take memos, and it can write code. And it has actually written code to improve itself. So this is the first example of artificial intelligence improving itself. Okay, I click the button and nothing happened. Click it again. Okay. It's also been described as the largest artificial neural network ever created. So it must be pretty big. Probably burns lots and lots of electricity. Yeah, and I'm going to skip over the quantum thing because that's a whole other discussion. Oh, damn. Let me back up now. In the past year, the industry has spent $46 billion on R&D. Next year, it's going to spend $53 billion on R&D. Google has 1,000 AI projects in the works right now. 1,000. They're not cheap. Watson from IBM offers over 30 services, all based on narrow artificial intelligence. It's got medical services it offers. It's got a legal service it offers. So a lot of people are being assisted by Watson in doing their jobs. Microsoft Salesforce, they use AI to find prospects and match them up with products and figure out what the products can do for those prospects to help them sell. The majority of revenue in chip manufacturers is all in synaptic processing units, neuromorphic chips, that kind of stuff, because that's where the money is being spent. And an AI guru, somebody who graduates from university with an advanced degree in artificial intelligence, gets a starting salary of over $100,000. So if you could go back to school and get your master's degree in AI, you could make a whole lot of money immediately, and even more if you're really good at it. I've got a universal translator on my phone. I think I mentioned this before. Google Translate. Please try it out. It's mind blowing. It can translate your spoken voice into any language in the world, just about. And if you can speak English and you go to Germany and you have this product and you meet somebody in Germany who has that product, you can speak English at them, they will hear German, and they can speak German at you, and you will hear English. Hot stuff. Hot stuff. Computers recently did better at sign recognition than humans. They actually did twice as well as humans in recognizing signs. Um, their error rate in image recognition is at 6% now. So if you show a computer a picture of a cat, there's a 6% chance it'll get it wrong, but a 94% chance it's going to get it right, which is better than people do. Google decided they were going to map every address in France. It took them 2 hours. These pictures have captions. The captions were all written by a computer. So this caption says, "Man in black shirt is playing guitar." Now, this is a computer that doesn't know what a man is, doesn't know what a shirt is, doesn't know what the color black is, doesn't know what a guitar is, and yet looked at this picture and formed that sentence. So again, very impressive, very impressive. Computers are currently able to identify cancer cells as well as doctors. So a doctor goes to school for most of his life, right? In medical school for what, 8 years or so, and comes out as a specialist in oncology. And after years of looking at x-rays, he can spot a tumor cell, and now computers can do it just as well as he can. But then again, this is really good because, it's nice to have a computer looking over the doctor's shoulder saying, "Hey, you missed one," right? That's a good thing. Another thing they did recently is they got better at predicting survival rates by looking at tumors, and a computer actually recognized that knowing what was going on in the cells around the tumor was just as important as knowing what the tumor was about. And that was something no human doctor had ever figured out. That was a new discovery made by a computer. They can figure out what neurons are by looking at them, what kind of neurons they are. This is just a whole bunch of stuff that don't worry about it. So what does all this imply for the next 10 years? Well, I'm going to skip this too, because, it's a lot of what we already talked about. What I really want to show you though, look what I did. It's hard to work these buttons when you can't look at them, Somehow I got to the beginning of my presentation. Rats. Well, what I was going to show you is in the next 10 years or so, what's going to happen is, because computers can see and computers can read and computers can recognize what's in a picture, and computers can speak multiple languages and can translate from one language to another and do all of these things. And they have access to all of the information available in the world on the internet and in databases. Computers are going to start, and they already have started, taking jobs that only humans could do 20 years ago. In the United States, in Canada, in Australia, in Europe, in Saudi Arabia, in the Netherlands, in Norway, in Greenland, 80% of the jobs are service related jobs. In all of those countries, in several countries in South America, all of those jobs, 80% of them, service related jobs. They're jobs that require you the ability to read and write and recognize correlations and all of this stuff I've been talking about that computers can now do. So in the next 10 years, what you can look forward to is massive amounts of layoffs happening of people that do service related jobs. The ones that are going to start going first are things like driving, sorting, checking out groceries, relatively easy jobs that are kind of manual labor oriented, but don't take a lot of strength. They're going to be replacing people with computers and robots. And it's happening now. So you can expect that that's going to be a rolling issue. Now we have to respond to this. We have to do something so that we're not all out of work and poor and starving to death, right? That would be a bad thing. But if we don't do anything about it, there's a possibility that could happen. And again, that would be a bad thing. But we've got AI getting really, really smart. We've got robots getting really capable. We've got 3D printers that can print anything you want to print as long as it's made out of metal or plastic or ceramic or oil paint. There's a lot of things you can print with now. Um, so we could be entering a golden age because if you look at our history, the history of mankind, we have lived through golden ages. And they all have one thing in common. The golden age of Greece, the golden age of Rome, what they had in common was nobody had to work except slaves. They had slaves do everything. The slaves did the farming. Well, AI and robotics and 3D printing means we could enter another golden age without human slaves or animal slaves, but with robotic slaves. And we would benefit from that of having a golden age. We could be going into an age when you don't have to work. Everything is basically free and abundant, and you can do what your heart is telling you to do. Go off and write that poem. Go off and paint that portrait. Go off and write that novel, right? Learn how to play the saxophone. That's what you really want to be doing instead of working for the man. Or it could get really bad. A dictator with a super intelligence at his behest could enslave his population. And there are already countries where the people are enslaved. And there are countries where everybody is under surveillance constantly right now. Everything they do and everything they say is being monitored and recorded and stored in databases. And they're all being watched. And imagine having a super AI helping you do that kind of thing. Imagine having super AI run your military and directing your weapons, which are all autonomous. Imagine the havoc you could wreak, right? So we could be going into dark ages too. So golden age, dark age. How do you control that? My most important message today is be really, really selective and careful about who you vote for. Because if you vote for somebody who's not qualified to address a problem like this, you voted for the wrong person. So that's my talk. I'm sorry I missed the last few slides. Thank you for being here. And does anybody have any questions or comments that they'd like to share? Anybody? Is anybody still awake? I guess that's the question I should ask first. Where are you? Okay.
Right.
Yeah.
You didn't even mention you were talking about recognizing the cat. Are you familiar with Google Lens?
Yeah, I played around with that. And, it's another one of those technologies, right?
Yep. No,
I mean,
I'm not talking about glasses
Oh yeah, where you can read a street sign in Chinese and see what street you're on and all of that stuff. Or I used it recently. I was well, not that recently. It's been a year since I was at the art studio, but I was at an art studio where I hang my work, and I asked if I could hang a work if it was a copy of a photograph from a magazine. Thanks, Ben. And she said, no, if it's a copy of a photograph from a magazine, we're worried about copyright issues. And I said, but there's a picture on the wall that I think was copied from a magazine. And I used Google Lens and I looked at it. And sure enough, it came up with the article and that a photograph that this guy had. And I showed it to the woman. And she said, oh, don't show me that. I don't want to know. But yeah, it works really well.
I use it to identify. People are always asking, "What kind of snake is this?" So I use it to identify snakes and
Oh, cool.
also like flowers and plants and stuff. It's real handy for it.
Yeah, I was wondering if there was one that recognized bird songs. I would really like that. Anybody else? Comments? Thoughts?
That would be Google Ear. That would be Google
Google
Ear.
Ear? Is there a
Yeah,
Google Ear?
No.
Damn, I didn't know that. Cool. Ozzy, did you have a question?
Actually, I have comments because this is a very interesting topic to me, and I like the way you augmented some of those things that you were talking about. I know them. I watched the AlphaGo movie and Kasparov and all those stories. I know somewhat information for like level average level. So I got into this artificial intelligence in October, and actually I'm studying on the course right now exactly what you were talking about. A lot of money there, and it's very interesting. And actually, I got lazy because I can't motivate myself because I have to work and study at the same time, and it's hard. They have a lot of different things like mathematics, like those probabilities, and different like Python, and all those things are new to me because I teach languages. So I kind of come from a different perspective. So it was like an experiment for me to jump to another whole level of studies and stuff. I feel so stupid sometimes, and I enjoy it because I haven't felt for a long time like that. Because I teach other people, and normally, yeah. So I study in Russia. It's University of Artificial Intelligence in Moscow. It's an online university. Yeah, well, I don't know how respectful they are around the world, but I think they have a branch in America now, and like they have very interesting like rules, and it feels like it's a real university. It's not like online courses where you just go and watch the videos. They actually have contests, like literature contests, and like different interesting paid like internships, and in the end, when it's actually a paid program, and it was around $15,000, around 90,000 rubles. For Russian scale, I think it's pretty expensive, but still, it was exactly like a university, like a course, 9-month courses. So.
Will you get a degree? Will you get a certificate at the end?
Yeah, it's an official certificate. What I wanted to show you is the list of my diploma works that I could choose from. And this is very interesting how they had, these are actual products and actual things that are already created. So the team of the university
hang
already
on just
did
a
that.
second. I would like you to do me a favor, and all of us a favor. If you click on this link here, where it says click here to subscribe, you can subscribe to my channel and join my Discord. Are you on a computer or a headset?
A PC, so I have to write down your Discord so I can find you.
That won't work. Well, the Discord name is Humanism.
Can you just send me the message so that way I don't misspell stuff?
I hate to type in this place. It's all point and poke,
I'm on PC, but I can click it.
You can click on that. Yeah. Did you get the pop-up? You don't get the pop-up.
No, it doesn't show a pop-up.
No. What you do on the PC, what you do is go to altspacevr.com in your browser and find the Vitruvian Man. That's my channel.
Humanism.
Subscribe to my channel and join my Discord, and then you can leave me messages in Discord, and everybody here who joins my Discord can see the message, and they can see all the information you post about the university and the courses, and then we all benefit from it. So that would be a good thing. if you don't mind.
It's even funny that maybe after some time, maybe I'll be teaching some lessons because they actually have a contest
That'd be
until
great.
tomorrow.
Yeah.
They look for people who can explain things and like teach things, and I'm a teacher, so I decided. And also, I know I speak English. I teach English, and maybe I could be a good, valuable asset for them to read lectures for like a universal, like international level. So what I wanted to tell you is about those projects that are being designed today. So, for example, you can put a camera on a drone that is flying. Yeah. This drone has a schedule when once a day it flies into a construction site, takes photographs from that picture, and actual AI architecture, it double checks these photographs and checks what is the progress for the construction. Well, they have new tiles this today and maybe 2 more rooms and brick walls, something. This is one of the AIs. The second one, it takes a photograph of an avocado, and actually it has to recognize, avocado, whether it's ripe or not. That's pretty difficult. I think I can't do that when I go to the shop. So they are going to have an architecture, which is probably a working project already, because if they give it as a topic for diploma work, it means like dissertation. It means that this architecture already exists and it should have pretty high levels. For example, there's this, I actually have done one work, was about the sonar. I've seen the actual work on Google Scholar. Actually, the sonar, it's a device that sends echoes underwater, and it measures depending on how quickly echo comes back to the device, it measures and kind of draws the landscape of ocean floor. That's what it does.
Oh, cool.
Pretty cool, huh?
Okay.
Yeah,
that's great. Could we let somebody else,
sure.
make a comment or ask a question or anything? Anybody?
The question I have is,
you sound like you're speaking in a tin can. I can give you the megaphone, but maybe you should try muting yourself and turning your mic back on. Try doing that.
Okay. All right.
That didn't work.
Okay, didn't work. You can't hear me.
I can hear you, but it's not very loud. Let me give you the megaphone so everybody can hear you. Go ahead.
All right, thanks. All right. So the question is, do you think it's possible that artificial intelligence might hit a plateau at some point and not be able to increase any further?
Oh, geez, I don't know. I mean, I've read articles where they talk about an artificial intelligence brain the size of a planet. Now, will we ever build anything that big? It's questionable. Why would you need a brain that smart? What would you be doing with it, right? And maybe that's a question I'm not even qualified to ask, because until we build a brain the size of New York City,
Yeah.
this is one of those things that we're just gonna have to wait and see. Is there an upper limit? Yeah, there probably is, because there are only so many atoms in the universe. Now, there's also the thought that any system, and this is the guy that wrote the book A New Science. Wish my brain worked better. I can't remember his name either, but he believes in cellular automata replicating the compute capability of any other thing that can compute. It's just a question of speed. And his way of thinking, the entire universe could be considered a cellular computer. Okay. And the thing that it's computing is the reality we live in. So is that the upper limit of how big a computer could be? I would say, yeah, probably. If the universe is a computer, that's it.
Right. The matrix, yeah.
Hey, thanks.
Yeah, I think that theory becomes more and more prominent recently about the illusory nature of our world, that it's something like a simulation, like in the Matrix. It requires a little bit more.
It's another conversation for another time.
Oh, yes, definitely.
Yeah.
What
I wish
about,
I could
what
think
do
of
you
that
think?
guy's name.
I have
Yeah,
a
go
question
ahead.
for you. Yeah, I
Yeah.
tried to Google, but I didn't find it. There are different books, but none of them has this name, new science. So the question is, what do you think about the new maths? I think Einstein and other scientists and physicists, they talk about the lack of this mathematical language that they need to kind of extend the physics. So do you think that is going to be the issue? Maybe we could use those computing powers to, or is it a clearly creative work? What do you think? Creating mathematics and mathematical formulas. Is it the machinery, calculation, or is it a creative process? What about this new maths that we really lack right now?
I'm not familiar with what you're talking about, so not qualified to have an opinion. Sorry.
Sure, okay, thanks.
Yeah. Anybody else? Thoughts? Questions? I see a hand. 64 degrees of what? Separation? Let me give you the, hang on just a second. Let me give you the megaphone. I don't see you in here. Oh, there you are. Okay. Got it. What's up?
Okay. Okay. You had mentioned that we should be aware of our politicians who are thinking ahead and trying to plan for such an event where the artificial intelligence will take over most of our jobs. Well, there is a candidate for president last year. Now he's running for mayor of New York, and his name is Andrew Yang, and he
Smart guy.
and he basically said that with the tax on artificial intelligence and robots and like that, we could pay for universal basic income that could
Right.
assist, not take over our total income, but can definitely assist on providing income and necessary sustenance so we won't be starving to death.
Yeah. Yeah, I subscribe to that. I would vote for that if it ever came up for a vote.
Yes, yeah, I was all for
You know,
it.
too bad Andrew didn't win the presidency
Yeah.
when he ran for it, you know. But
Mhm.
you know, the thing that scares me is when you see the guy in the Senate who's you know, the head of the science committee coming into the Senate with a snowball saying, I have a snowball, therefore there is no global climate change. You know, guys like that, it's like, give me a break. How are we going to survive if he's making the determinations?
Right.
So, anybody else? Thoughts? Fears? Is your hand up or are you just saying hi?
Oh, my hand's up.
Polyglot. Yeah, what's up?
Hey. Well, firstly, comment on what we would use a planet-sized computer for. I can think at least one thing: figuring out to calculate the answer to the meaning of life, the universe, and everything.
42.
Exactly.
Everybody knows that. Everybody knows that. Could you give her a hand?
I don't know why it keeps floating away. I have no idea.
I can't find my hands. Oh, there's one. Is the other one somewhere? I don't know.
Just kidding.
I don't have hands. I only see one, so I'm like Anakin Skywalker right now. But anyways, piggybacking on the conversation about politics and AI. With our last president, he was really emphasizing bringing manufacturing jobs back home and emphasize greatly the jobs that are more manual labor new type. Do you think that is the wrong direction to go into? To emphasize, no, we need to have humans in America doing these things rather than preparing for when artificial intelligence is just going to wipe all those out.
What do you think?
I think, well, I personally think that it's the wrong direction to go in. It's clinging onto the past when the future is on its way to us. Even if we do manage to bring all those jobs back to the States, we build all the as soon as factories start making money, the factory owner is going to start replacing those workers with robots, and especially once the singularity hits, I mean, there's really not going to be any reason for these factories to keep these workers around, unless there's like something really specific that humans can do that the AI isn't able to do. But there was a there was a social experiment done in Kentucky, I think it was. I'd have to look back up, but uh, they I think it was done where I think it was where there was like no tax or something like that on the business. I can't remember what it was, but either way, it was made to where businesses had more money, where theoretically they could pay their workers more, but instead they invested in robots to increase their profit margins even further. So I personally see it as a short-term solution to a long-term problem, and that really we should be focusing more on how to prepare for when robots are taking care of most of our entry-level positions, and even some of our major really high-level positions.
Well, we're going through a period right now of cooperative computing where, a doctor can use Watson to make himself a better doctor, and that's a good thing, right? So if I was a doctor, I don't think I'd be too scared, because even if you were just supervising a robot doing surgery, you have a job supervising a robot that's doing surgery, and they're probably not going to take the human out of that scenario. But would there are a lot of jobs like being a checkout person in a grocery store. There are grocery stores now with no people working in them at all. You get scanned when you walk in. Cameras watch what you pick out, and the bill is emailed to you when you walk out the door. So who needs people there? So anybody who does that for a living, and robots can stock the shelves. That's not a problem. So there's a bunch of jobs that are just going to disappear, and it's going to be devastating as they start to fall away. The COVID-19 pandemic opened a lot of eyes of people who had thought they had good careers and good jobs, and now they don't. And a lot of them have jobs that are never going to come back. And they're all sitting on their hands saying, what am I supposed to do now? And they're angry, and they're acting out their anger. And okay, I get that, but that's not a solution to the problem. Somebody has to start thinking about a solution, right?
What sort of fields and jobs do you think would be good to invest in for like if let's say someone's trying to decide what to major in college, or they want to make a career change? What sort of jobs do you think would be a good bet or a good investment for the next 10 years or so, or even the next 5 years?
That's really hard. I've read a bunch of articles on the topic, and what they recommend is jobs that require empathy, because you're not going to get empathy from a machine. So being a nurse is a good job because it's highly skilled. It takes intelligence, but it also takes empathy. And you could build a robot that can carry a patient, but you can't build a robot that's going to make them feel like somebody cares about them, right? Actually, I have a presentation on that. I should probably come back with that at some point, because that's all I talk about is universal basic income and which jobs will actually survive for a while. But there is going to be a time when working is going to be absolutely optional.
You always need plumbers.
We'll always need plumbers. Right?
Solid point.
Yeah.
I find the most fascinating thing about all this is the changes in real estate. Like apparently in New York and San Francisco, they're throwing in a month of free rent. But the big problem they have now, apparently at Facebook, is that people are leaving San Francisco like crazy, but they're still getting the same pay for moving to Idaho or Nevada. Whereas there's this debate about if you move to Nevada or to Idaho, technically you should have lower pay. But then other people say, well, they're doing the same job, even though the cost of living is lower.
Yeah. Yeah. When I worked at Bell Laboratories, what their philosophy was your pay had a cost of living attachment to it. So if I worked in Illinois, that would vary based on where you lived. So they were doing that 40 years ago. How much you got paid depended on where you lived. So there was your salary, and then there was that cost of living piece on top of it. But my son did the same thing. He lived in Washington, D.C., or very close to it, Crystal City. And he just moved up to upstate New York because they're paying him the same money. And the cost of living in upstate New York is like 2/3 of what it was in Crystal City. Doing the same job, does it remotely, makes the same money. It's much better for him. So yeah, I think you're going to see a lot of that. The whole infrastructure as it used to be when I was in the workforce. I used to drive up the parkway with thousands of other people driving north, and on the other side of the divider there would be thousands of people driving south. And I always sat there thinking, if I could only find one of those guys who would trade jobs with me, neither one of us would have to go anywhere. Right? But working at home solves that problem too. So what's that going to do when you have autonomous vehicles? Is anybody going to buy a car anymore? Because why would you? Right? Just take out your phone and say, hey, smart device, get me a car. And then an autonomous car pulls up in front of your house and it takes you where you want to go, and you tell it where you want to go. And then you get out and it goes away and it picks somebody else up. Why would you buy a car and pay insurance and, deal with repairs and breakdowns and stopping for gas and, all that bullshit? Why do that? And I think we're going to go through a whole phase of all that stuff disappearing. Thousands of cars going north every morning at 9 a.m., 8 a.m. That's going to stop or slow down.
Point.
Well, good, because we need to reduce the number of cars on the road if we want to combat climate change, Annie.
Oh, yeah, well, yep. That's another problem, right? No. Emin, you haven't said boo. Still there? The lights are on, but nobody's home.
Yeah, I joined like literally 10 minutes ago. I had an event.
Oh.
Sorry.
Well, I hope it went well. Do you have comments or questions or anything? No, you're good? Okay. Well, thanks for coming, folks. You've been here a long time. 2 hours and 19 minutes. You guys are tough, I'll tell you.
Time flies.
But my wife knows I do this, and she wants to know why your legs aren't all tired. How can you stand up for that long? Right. So, there it goes again. Wish I could grab it.
That's cool.
So if you haven't signed up for my channel, please do, because then you won't miss the next talk and stuff like that. And hopefully you join the Discord as well. I'm getting an echo.
I think I have to change my battery.
Oh. Yeah, that's probably it. You're running out of battery in that hand.
Something like that. You had mentioned when we first came in that there was that Japanese designer.
Oh yeah. You want me to take you there?
If you wouldn't mind, I'd love to.
Not at all. Let me pull that up. And anybody else who wants to come along, you're welcome to. Where I am taking her is to the work of somebody who is considered to be one of the very best world builders in all of alt space. And he is good. That's not it. I got too many of these.
Ah.
Tectonic mirror.
Yeah. Everybody in who wants to be in? Here we go.